Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to take an in-depth look at the environment class. Remember that the environment is the thing that the agent interacts with. Let's start with an overview of all the methods we're going to look at. There's the constructor, where we initialize important instance variables. There's isEmpty, which tells us if a location on the board is empty or not. There's reward, which gives us back a reward when we pass it the symbol representing a specific player. There's getState, which we looked at earlier. It takes the state of the board and returns a number. There's gameOver, which checks if the game is over or not by looking at the state of the game and returns true or false. And there's drawBoard, which draws the current tic-tac-toe board. You can imagine that this would be pretty pointless if we could not see the tic-tac-toe board. Let's start with the constructor, since this will introduce us to all of the instance variables we're interested in. The first instance variable is the board, which is a square. We initialize it as zeros because 0 is going to be our symbol for empty. Next, we define the symbols for X and O. Note that these all have to be numbers, since we're storing them in a NumPy array. You'll see why assigning them to +1 and -1 is convenient for us later on. Next, we have the winner, which we initialize to none. None means there is no winner, or that there is no winner yet. Once we do have a winner, we'll assign this to either +1 or -1. Next, we have the Boolean variable ended. This is obviously going to start out as false, and will only become true at the end of a game. Lastly, we have a variable called numStates, which is just a convenience thing, so we don't have to write 3 to the power length times length everywhere. Next, we have the isEmpty function, which takes in 2 arguments which represent a position on the board. This is a useful function for the agent because the agent needs to check if a location is valid before trying to put down one of its own pieces. So this returns true if that position on the board is 0 and false otherwise. Next, we have the reward function. As we stated before, the reward is 1 if we win the game, otherwise the reward is 0. Reinforcement learning is defined such that a reward is given as feedback on every state transition, so we need to have this function be able to return a valid result in every case, which is why we can't just call it when the game is over. When an agent calls this function, it'll need to pass in its own symbol, which tells us that each agent will need to know its own symbol. Now we get to the more complex functions. We've actually already seen getState earlier in the course when we talked about enumerating states. The idea is that if we order the states as base 3 digits, then the entire thing is a base 3 number, and we can convert that into 1 decimal number. So that's what this is doing. Next, we have the gameOver function. This is probably the most complex function in the environment class. We have this force recalculate argument you might be wondering about. First, you'll notice that gameOver is called multiple times in this script. If a game has ended already, we don't want to do this complicated operation again and again, so we just use the fact that it's already ended as a shortcut. But if you recall in our earlier recursive function to enumerate the states, we recursively filled out each location on the board. This involves placing pieces on the board, taking them off, placing other pieces, and so on. So we are going to go back and forth between a gameOver state and a non-gameOver state, which means we can't use that shortcut. So force recalculate allows us to make sure the entire operation happens every time. The next parts of the gameOver function are as expected. We check if there's a winner, and if there's no winner, we check if the board is full, which means it's a draw. We check for a winner by first checking all the rows, then all the columns, and then the diagonals. This is where assigning the values of X and O to be -1 and +1 really helps us. Since if we ever have 3 X's in a row, the sum will be -3, and if we have 3 O's in a row, the sum will be +3. If we do find a winner, we then set the winner instance variable to the player that won, and we set the ended instance variable to be true. We also return true, since the game over function needs to return a boolean. The only place where this is slightly non-trivial is when we check the diagonals. We know that the trace of a matrix is the sum of all the elements along the main diagonal. So doing the trace will give us the sum from the top left to bottom right. But what about the sum from the top right to bottom left? In order to use trace here, we need to first flip the matrix and then do the trace. For checking if there is a draw, this is a function that checks if all elements on the board are simultaneously non-zero. In this case, we explicitly set the winner to none, even though winner might already be none, since that's what we set it as in the constructor. The reason we want to set the winner explicitly is that when we call this function, it's possible that it is a recalculation, so winner might have previously been set to something else, in which case we would want to set it to its current value. Finally, at the end, if none of the above conditions are true, we return false. Lastly, we have a function called drawBoard, which helps us visualize the tic-tac-toe game. In fact, it would probably be pretty hard to play tic-tac-toe if you couldn't see it. So this just loops through every position on the board and places the correct symbol in the correct position.